Hello, my name is Ed, and I will be presenting to you today defensive programming best practices. So, the target audience for this webinar is scientists who have a bit of a background in programming, but not necessarily a formal education in programming. You've learned a language, you've made a few programs, but when you go to refactor them or debug them, or you make anything that's any bit more monolithic, you start running into problems. So what you're often missing from a formal programming education is a software engineering viewpoint. And that's what this webinar is going to be about. While we're not going to focus on any particular language, it is going to be very object-oriented, and it is going to be a little Java-centric, though the ideas presented in this webinar do apply to all programming languages. Now, in any programming project of a non-trivial size, regardless of the skill of the programmer, bugs are going to creep into your code. And by bugs, it's not necessarily it's going to be unforeseen circumstances, it's going to be programmer error, etc. Now, careful planning, correct practices, and simple elbow grease will help reduce their occurrence. However, if you follow a few basic practices using the appropriate design patterns and systematic testing, you can help mitigate the occurrence of these bugs. In this following webinar, I'm going to show you a few practices. Some of them are simple, some of them a bit more complex, that will help you either avoid buggy code, make it easier to debug, or refactor your code. Now, arguably, the goal of good programming practices is to protect the programmer from themselves. The programmer is their own worst enemy. And no one's going to write perfect software in one pass. What I have here is a development process. And you'll notice the development process is circular. You're going to write your code. You're going to test your code. You're going to repair what the test found to be wrong. You're going to tune it. And then you're going to get redefined, or it's going to get redefined for you. Or you're going to expand on it. You're going to write again. You're going to test. And it's a very organic process of testing, fixing, tuning. It's been said that you always write your software twice. The first time you write it is to learn what you're doing, and the second time is you write what you intended to write the first time. So what we're going to cover here today is often called defensive programming, and it is the philosophy of writing code with the intention of handling the unintended, the unforeseen errors, bugs, and circumstances. And that means we're going to have a series of practices that will not necessarily improve your code, but will help you refactor it. By refactor it, I mean rewrite, help it find bugs, try to foresee or try to understand when bugs are going to occur, and when they do occur, write code so that it's easier to find out how to fix these bugs. So there are goals of defensive programming, and the first is correctness. And when I say correctness, your program has to do what you say it's going to do. If it doesn't do that, you've missed the entire point. I can make a fast, small program that doesn't do what it's supposed to. That's not the goal. Second goal is clarity. That means it does what it's supposed to do concisely, which brings us to readability, and the same thing there. And that means that other people, and more importantly yourself, weeks or months on, can read the code. They can understand what's going on, and the less time it takes to read the code to understanding, the better. And another goal, of course, is bug prevention. So the first three are basically trying to foresee, trying to write better, and then we're just going to try to do some things that will help you not write the bugs in the first place. There are three things we don't do when defensive programming, and that's code for speed. Code for speed after you've written your program. Then you'll benchmark your program, figure out where the bottlenecks are, and try to optimize those parts. And this is known as early optimization. And that is doing things without knowing what needs to be optimized, or optimizing without knowing where to do the optimization. And this is, more than anything, it's a waste of time. And secondly, when you start optimizing code, you start getting rid of clarity, readability, and your bug prevention mechanisms. And what usually causes these errors is cleverness on the part of the programmer. Don't try to be novel at all times. Try to make your code clear and concise, and try and make the overall algorithm, save that for the cleverness. Once you start getting clever, it starts to get hard to read and hard to code. So we're going to try and focus on very practical programming aspects. So this webinar is divided into 3 parts. And the first part is going to be a short introduction to object-oriented programming. Now, object-oriented programming, which is supported by languages such as C++ and Java, is not just a language. It is also a design philosophy. It involves dividing up your code in such a way to small, well-defined chunks and well specifying how those pieces interact with each other. So we're going to introduce a short introduction on a few things: UML, Unified Modeling Language, and then some object-oriented principles: abstraction, encapsulation, inheritance being the 3 big object-oriented principles. Cohesion and coupling are metrics by which to measure your program and how well it's been put together. And then we will also introduce the idea of design patterns. And the idea of this is not a comprehensive lesson on object-oriented programming, but rather gives you a starting point if you're not used to it. So the Unified Modeling Language, often known as UML, consists of a number of methods and diagrams for abstracting your code in such a way that you can understand the metacode, or what's going on outside of the implementation. Now, we're going to specifically focus on class diagrams, but UML is a general purpose developmental and modeling language used by software engineers that provides a way to visualize the design of the system. What we're going to be looking at here with class diagrams is more how to visualize the implementation without doing the implementation, the details of the methods in the interfaces. So what we have then is these are known as class diagrams, and the lines between them are the associations. That means that one class or one module, often classes, is associated with another. And then sometimes you'll get arrows, which will show a direction association, and there will be numbers here which will show cardinality, which we'll cover in a moment. The goal here is to provide an implementation-independent description of the data and the methods that work on the data that you're going to use in your system and are passed between the components. So abstraction. Abstraction is the first principle of object-oriented programming. And the goal of abstraction is to reduce the complexity of an object by only exposing the relevant properties. Now, what that means is, if I were to say give you a calculator, this is a class diagram for a calculator. It has the name of the class. We have defined some values in here, some parameters. Value we've made public, more for the point of example with a plus sign, and negative means it's private. What we are exposing are down below here are known as the methods. And these are, the pluses means that it's public to the user, minus is more information for the library implementer. So the goal here is that what I haven't defined is how I've coded add, how I've coded divide, etc., etc. So if you are saving values inside and you're using a linked list, you wouldn't mention that in this case. You want to keep it completely abstract. The next part, now abstraction, leads to encapsulation. The goal of encapsulation, which is moderately, they're all related to each other, it's related to abstraction, is you want to restrict access to the components of the object through the use of methods or through the use of accessors. I need to shrink that. So what we see here is we've got an object basket. The object basket has a collection with a association, and it also has an association with fruit. Now these are two UML connectors. The one on the bottom here with just a line is known as a simple association, and it is a broad term encompassing any relationship between two classes. Now I have associated with fruit. That means they are moderately dependent on each other in that basket takes a collection of type fruit. The second one is a composition, and it is a life cycle dependence association. That means that inside of basket I have created a collection called fruit. The fact that this arrow, it's this type of arrow, means that when basket ceases to exist, this particular collection will cease to exist. And what we're trying to show here is encapsulation. I have encapsulated collection into basket and hidden that from the end user. That means that while the collection has get, has set, which further encapsulates an array inside of it, the end user of my library, my program, is not going to see this. And these are going to be accessed through the methods of basket. It gives me more control over what is inside the basket, and allows me to swap things in and out because the end user doesn't know that it's a collection. Another way of achieving abstraction is through inheritance. Unlike encapsulation, which seeks to build building blocks or wrap other objects inside of an object, this is inheritance. It means a child class assumes the functionality of a parent class. Those familiar with Java, this is an extends class. So what happens is, as before, we had a collection that was a member variable or a member parameter of basket. We now have a collection. It's a different arrow. You'll notice the endpoint is different, and it means that collection has been extended to become basket. So basket has taken on all of the properties of collection, and this is where the private and public matter. As the basket still will not see the private members of collection, it will just see the public members, get and add. And then it can add things to it. Adding fruit has space and empty, so that means anybody using basket still has access to the get and add, but also has access to further objects that basket has added. We have also changed, this is a contains. So basket contains fruit, and it's got a cardinality. That means that each fruit is in exactly one basket, and each basket can have 0 or more fruit. It's known as an aggregation. Now, if this were not a filled-in diamond, it would mean that it was, and it's not supposed to be, it means it's not life cycle dependent. It means that the fruit was added by an external source and would be cleared, memory collected, etc., also by the external source. Now, those are the three principles of object orientation. Now there's two metrics, the first of which is cohesion. When we talk about cohesion, we're talking about the amount to which the components of an object relate to each other. How much do the methods interact? How much do they matter? So if you have several parameters in your method, and only some methods, several parameters in your class, and only some methods are using those parameters and some methods are using other parameters, you would have a low cohesion. If all of your methods use all of the parameters, they're all interacting well, it's high cohesion. And the goal is to increase the cohesion of the class. And that often means if you look at a class and you see there's two different things going on, you can split it into two different classes and then use encapsulation or abstraction in order to merge them later on. And this will make it easier to refactor your code. Now, on the opposite end of cohesion is coupling. And when we speak about coupling, we're talking about how much two objects or two classes are dependent on each other's methods or each other's behavior. And the goal is to reduce coupling. So you want a high cohesion within a class and minimal coupling between classes. Now, of course, because the program is meant to do something, there is going to be coupling. The classes are going to interact. And you want to design your classes in such a way as to minimize the interaction between them while maximizing the interaction within them. And this is often generalized in what are called design patterns. Design patterns are a software engineering idea that creates formalized and recognized practices for solving programming problems while designing an application. Now, these are not code. These are not pre-done code, not libraries. These are ideas and terminology that you can use to both communicate with yourself in comments, etc., or communicate between programmers. And there are a large number of these. Here we have divided them into 4 different subcategories of patterns. You got structural patterns, which means how you're going to lay out your code. Behavioral patterns, what your code does. Parallel patterns is actually a structural pattern, but specifically for parallel programming. And concurrency patterns are behavioral patterns, specifically for parallel programming. Some of these you may be very familiar with, and you've probably already used. MapReduced is a whole paradigm unto itself for data processing. Mutual exclusion locks are familiar from just about all programming languages. And read-write locks are an extension of mutual exclusion locks. And then you'll have things like NULL objects. Strategy pattern we're going to introduce today. Iterator is built into a language, such as Java has built-in iterators now, JavaScript. So some of these things are considered ways of communication, but some of them have also been built into languages and are no longer as relevant as they used to be. They're no longer patterns that you need to specifically declare, which is part of the criticism of design patterns you'll hear once in a while. Now, that was a brief introduction to object-oriented programming, and mostly so that you understand the language of the next parts. In this part, we're going to talk about style. We're going to talk about modularity and how to avoid long bits of code. We're going to talk about naming conventions. We're going to specifically talk about in a Java type of naming convention, but it applies to all languages. We're going to talk about the use of collections over arrays, and that's a very object-oriented principle. And to use iterators, which are now language supported. So modularity and the avoidance of long code blocks. The goal of modularity is readability. It makes things readable. People will argue that method calls and function calls reduces performance. But we are not concerning ourselves with performance. We are concerning ourselves with whether or not we can understand what's going on in the code. It means it makes the code less readable, it's less buggy, and easy to refactor. So we're going to talk about this particular bit of code right now. So on the left-hand side is a long chain of if, else if blocks, which is fairly typical. You almost, on your first write, will almost always do this because you're just adding things you're looking at. You haven't necessarily designed your code properly. But when you refactor, and your goal is to get what you have on the left. So what we've done here is, well, on the right. What we've done here is on the left, we've got comments to describe what's going on in the code. And that kind of breaks up the flow of the code. And we won't necessarily see that you can't immediately see it's an if, else, if block with the comments in there. On the left-hand side, we are going to try and use appropriate method names that will describe what is going on in that block, and we will extract the code that was inside the if statement into a method. Now we've got one line if statements, and we can clearly see it's an if, else if block. And if we want further information, or where the comments would go, we would now take the comments and put them down to the methods, so that it's not breaking up the program flow, making it readable, and making it obvious if a mistake has been made. Now you'll notice in the last slide I talked about naming and naming appropriately. And this is one of the big things that will often slip when you're in the throes of programming something. And naming conventions are academically a set of rules for naming methods, variables, classes, etc., which allow the reader to quickly identify the purpose of the particular identifier. Now, when I say the purpose of the particular identifier, I don't strictly mean what the method does. You may want to know what the method does, but you may also know, is it a method? Is it a variable? Is it a class name? Is it a package? That means where in the language, what's the semantics of what it's being named? What's the semantics of the variable, as well as what it does? So when doing these things, you often don't have spaces in your variable names for a language. So we got to figure out how to do multi-word variables. So a typical way is letter-separated words, such as camel case. And that means that the first letter of each subsequent word, that's not the first, is capitalized. There is also Pascal case, which is very similar to camel case, except the very first word also has a capital. There is delimitated separated words, such as here with the underscore. The underscore is known as a delimitator. There is pre or postfix notation, and that means you have stuck something on the front of it. This is very common in JavaScript, which doesn't have private variables or private members, so the people will often put double underlines in front. That means this is not to be messed with, or this is a private member, so that it may change. Do not rely upon its performance. A word prefix, you can go int salary to let you know it's a salary, or float salary, or string salary, or something like that. You also use prefix notation sometimes when declaring interfaces and abstract classes, such as I or A in a capitalization. There's also often rules that apply to all of your variable declarations. Sometimes these are language enforced, sometimes they're not. No numbers. Certain things should be nouns, variables should be nouns, methods should be verbs, or start with a verb, etc. Now, when we say naming convention, you need to understand that these are not naming rules. Conventions are things that are laid down or set down either by yourself or by somebody else who has declared what programming you need to do and can change. Although, generally speaking, conventions are shared across different paradigms. So once you see some way, they're often, a lot of people are going to understand that that's how they're done, and you should probably adapt them yourself. Here are some examples of naming conventions in readability, which is what we're getting at. So, for this top one here, A equals B times C. And you'll see that everywhere where you see math in a program. Instead of using A, B, and C, pay equals wage times hours, you almost immediately know what's going on with the code. Another example, which I had mentioned earlier, was to put the prefix of a letter before the name. So interface I collection or abstract A collection. That way later on in the code you can understand that when you're making these classes or you're creating instances of these classes, whether or not they're concrete classes, interfaces, or abstract classes. You will also often see interface has context or interface is context, which is implying that it has certain properties, whatever the context properties would be. Now here, in the for statement, and down below in the for statement, you'll notice that I did use I, and X, and Y. And oftentimes, in iterators, or when iterating through an object, you will use common single-letter variable names. And this is perfectly acceptable, because in long for statements that you get in Java and C, it can be very difficult to read if you have long variable names in there. When we use I, we almost always know that we're referring to an index. When we use X and Y, we're almost always referring to a matrix. X being the horizontal and Y being the vertical. Over here we have class declaration. And you'll notice I'm just going to point out some of the different things that you have to pay attention to for naming conventions. So I forgot the class name, but there would be a class name. You have a method name. You'll notice that the method name is in camel case. Float per hour wage. Very clear on what it is, not just float amount. I'll often have, in languages that are object-oriented, where you have private member variables, this dot wage is equal to, that should be per hour wage. And you'll notice that it's still lowercase, because oftentimes for a variable name, lowercase, for a method name, lowercase, for a class, uppercase, etc. We are now going to do one more demonstration of naming conventions. So here we are. Here is a typical Java class kind of code. And we've got a number of different levels and their typical naming conventions. So at the first, we have a package of fruit, which is lowercase. Often the packages are put in lowercase. You will, if you do an import, the tree of the package, java.awt, is in lowercase. However, the final class name is in uppercase, and that's for your import. Now note the java.awt is the name of the library. If you make your own library or your own class tree, what you'll typically use is the reverse of your web address where you store it. So if you have your own web address that you own, so you would say sharcnet.ca, your code would be ca.sharcnet.library path. And that way you know that it won't conflict with other people's library paths or other things that you've written. So maybe you'll do ca.sharcnet.ed, your library path. Is to prevent conflicts. Public class fruit, you'll see that it's a capital F, implements iFood, which has the I to indicate that it's an interface. Again, it's not required, it is a convention. Static final display resolution equals 640. This is a global. It's a global that you would see in Java because it's static, final, and public, even though this is protected, not public. And it would be the same as a global variable in C. Now, you don't want to use, this is to replace what's known as magic numbers. If you've got a number in your code that's not immediately obvious, you want to give it a name. And you want to make it very, very clear that this name is a constant. It is something that could change. It is something that means something in the real world. And its display resolution equals 640 here. And that means clearly it's the display resolution of your monitor or whatever this class is for, is 640. Instead of putting 640 in your code, so that now if we want to change it to 1280, we only have to change it in one spot. And then every time you see that number, you know exactly it means display resolution, as opposed to seeing a magic number in your code. Variables, so private flavor, private color, and private shape. The reason I did that there is oftentimes a flavor is just a flavor, and color is color. So you will match up the variable name with the class name and drop the first capitalization. Perfectly acceptable. Method names, in this case, public fruit, capitalized because it's a constructor, and it's the name of the class. It's language defined here. Public void ripen, you'll note the lowercase. And of course, public void add to basket, the camel case. Passing in basket, you might not have a specific word for the basket, so we'll pass in the name of the class. Keep in mind, when you're choosing these names, and you might not often have an appropriate name right away, you might want to change the name later on, try to choose something that's easy to search and replace on your particular IDE, something that you can do a find on that's going to find just that and not necessarily partials. So that's why usually multi-word identifiers are good, because they're not often part of another identifier, making search and replace easy and finding the bugs for the bad replacements quick. So this is an example from the book Essential Java. And it's a bug in here. And it's a very common bug. I'm sure everyone who has done any amount of programming has or will do this mistake. And this mistake is typically caused as a cut and paste error. You're doing something, you're working, you cut and pasted some code, it looks right, but it's not. And what is happening here is we have gotten rid of the curly bracket delimiters for blocks, which is completely valid, and we're using for loops, which can get quite messy to read. We have done a new card, I next and J next, this line here. What we are trying to do with this code is populate a deck of cards. So we've got the suits, we've got the ranks, and we want to iterate through it for every suit and for every rank, create a card. Now here, because we go I next to J next, this is known as an iterator, is iterating from, it'll go club ace, diamond deuce, heart 3, etc., because it's iterating each one every instance of the inner loop. And this is very common, and the best way to avoid this is to use a language implemented iterator and to include scoping brackets. So the scoping brackets, these are the curly braces, make it a lot easier to understand where the code is and what's doing what. Although it adds a couple of lines to your code, it's generally your general practice should be to use them as opposed to not, especially if your code is going to be, or the logic is going to be on a different line than the iterator. There's a famous Apple mistake that came out recently, or last year, which didn't use code braces and completely crashed the program. Anyways, back to the problem at hand. So what have we done? We have now got two selections of suits here, the same as before, but now we're using iterators, which means we use names. So we've got named suit, named rank. It's easier to use, easier to read, and we create a new card each time. So we can see that the brackets, we're not declaring next. The next is done automatically by the iterator. So when possible, use language-supported conventions, not necessarily because they're faster, but because they're easier to read and they're less likely to introduce bugs. It's very difficult to introduce the same bug as before when using language-supported iterators. Now we are going to move on to part 3. Now this is patterns and practices. As opposed to parts 1 and 2, where we were talking about particular styles, here we are talking about specific practices. And now these do not necessarily, these are going to be a bit more Java-centric, and they're going to maybe apply specifically to different languages, but they are going to be common practices that you can do to help reduce errors in your code. We will go through exceptional circumstances, which is a fancy way of doing return values or letting responses from your methods and functions. We're going to talk about the evils of the null value, the equals, interfaces, the strategy pattern, and stateless objects. An exceptional circumstance. An exceptional circumstance is something that has happened to your code that you didn't want, or it's not normal to the flow. So this means you tried to open a file, the file wasn't there. That is not normal. That is not what you expect to happen. A dropped internet connection, stuff like that. And there are 3 ways of alerting the programmer or the user of your code to exceptional circumstances. The user could also be you. Keep that in mind. The first way is assert. Now an assert is something you're doing while you're designing your code, typically. It's things that should never occur. It's to protect against programming errors. It is to make sure that methods are private. It is to make sure that return values are validated. And these are things that you can often take out once you are done coding. Exceptions, these are actual throwing of an exception. So an assert will throw its own exception, usually terminate the code. An exception is something that, a caught exception would be a better way of saying this, is something you want to let the end user know, and it's uncommon conditions that are out of your control. So it's not something that you could say, oh, I was passing a value that wasn't legal. That would be caught by assert. Here we're catching the missing files, dropped connections, stuff like that. Now I put return value in here. Now this is not, typically you will do a return value in two cases. One, you're using C, where exceptions aren't available. You should use long jumps, which you shouldn't use. Or the situation isn't terminal. Maybe it's just a case that is going to change the branch. We strongly recommend not indicating exceptional circumstances through a return value. And a good example of this that is C's malloc. Do you always check the value of the return? Not necessarily. So, or the printf. Printf has a return value, so does scanf. Most people don't check it. So what you should be returning are values are requested information in exceptional circumstances. When the language supports it, mention it through an exception. Now we're going to get into null. Now null is a four-letter word in my world, and it was known as the billion-dollar mistake. The invention of the null reference in 1965 by Richard Hoare. At that time, I was designing OWL. I couldn't resist the temptation to put in a null reference simply because it was so easy to implement. This has led to innumerable errors, vulnerabilities, system crashes, which have probably cost $1 billion of pain and damage in the last 40 years. The inventor of the null reference. The null reference, for those who are not necessarily familiar, doesn't mean everything. It means an unset value. It doesn't mean 0. It means, it was for C, as often means an unset pointer. And it is dangerous because of the fact that it doesn't actually have a meaning. It simply means unset or not declared. JavaScript has gone one deeper, and now they've got undefined and null. So now you've got something that says it's undefined, and we've defined it as undefined, and still dangerous. And I'm going to show you some examples of why null is dangerous. But first, some guidelines to using null, when you should use null, when you can keep it safe. So only use null privately in a class. So that means use it within a method where you have absolute control over when something is null or when something is unset. So say you initialize a variable, you can initialize it to null within the method, so long as you never return that variable directly, or would return it through a getter or a setter. So don't return nulls. And if you never return nulls, you never have to check for null. When an exception, when a null is passed into a method, you can check this with asserts. Check if it's null, throw an exception. That way you know, oh, a value was returned. That was incorrect. If I never return a null value and a method gets a null value in, something has gone wrong. We've caught it at design time. Return empty collections or zero-length arrays and return null representative objects. This means choose your objects, choose your return values appropriately so you don't have to return null. When you return an empty collection or a zero-length array, you can still iterate over the collection or the zero-length array. It just won't do anything, but it makes the code itself valid. Returning null representative objects. If I want an object that returns something, but if that object isn't there, it means unset. Then you return a null representative. That means that the methods are still applicable to the object. If I return null instead of an object, if I run a method on that, or if I try to call a method on a null, I'm going to get an error. If I call a method on a null representative object, it's going to have defined behavior. So that means we have defined behavior on an object as opposed to undefined behavior. So, return empty collections. Here's a code example of returning empty collections. In the class, on the left-hand side, we return null. This is a very common practice. If collection size is 0, return null. Forget fruit. This is in our basket class. So we try and get something. There's nothing in there, so we can't get it. We're going to return null. In main, when you go fruit f is equal to get fruit, this is not, you have to rely on the implementer or the user of your code to check for null. If null is not, if f is not equal to null, then you iterate through your array. So you're relying on the end user to check. They're not necessarily going to. What you can do instead, if they don't, they're going to get an error. Do instead, in the class, if collection.size is equal to 0, so that means there's nothing in the collection, return a zero-length array. Assuming your language supports it, most modern languages do. In main then, we can now use the iterator. We can iterate for every f in getFruit, do something. If it's 0, we don't have to check for null. It's just not going to do anything because there's no f's in getFruit. Much safer. And another interesting way about this is I was mentioning about scope levels earlier, and a lot of people like to skip these little curly brackets because they don't look nice. They don't necessarily add to the flow. Doing it the collection way, or doing it the empty collection way, reduces the number of scope levels, making your code more readable. A single instance. So, and this is a single instance, not a collection. Inside of class basket is an array list. If you have fruits.size equals 0 and you return null, you are typically going to document this somewhere, usually in a comment or in a doc, and it's going to say if size equals 0 will return null. Beyond the documentation, null has no inherent meaning. What you are really trying to impart here is the information that there is no fruit. The basket is empty. So we have tried to remove it. It would fail. Or you return the fruit. If it fails, null has no value. Null does not inherently say the basket is empty. What you should do as a designer of the class is force the user to check if the basket is empty. Because the check is going to have to take place anyways, the null check. So you might as well force them to do it. And the way you do this is by having a hasFruit method, or a contains, or some sort of method that checks whether or not your particular container contains any objects. And then the user will call hasFruit, if hasFruit, getFruit. Now you'll notice that we have done the check inside the method as opposed to relying on the end user to check. So if they have used hasFruit, it is now considered, we now consider it illegal to call getFruit if hasFruit returns false, and we will throw a null pointer exception, or whichever exception you consider appropriate. Otherwise, we'll return fruit. And this comes into null misrepresenting errors. And now I keep referring to users checking for null. When you rely on the user to check for null, they might not. And you can throw an error. If you do so, or if an error is thrown, it often doesn't throw where the error occurred. It often gets thrown where you first use the data that you have set to null. So it might return null. That's where the error actually occurs. You don't discover it until you check it. So in this case, we have got a piece of fruit is equal to getFruit. We're going to do some stuff, often maybe 100 lines of code in there, and then we are going to use a piece of fruit.eat. We're going to call a method on a piece of fruit. Well, this, if has returned null that we forgot to check, is going to throw an exception or throw an error. And you're going to have to search through all of your code to find out here that you didn't check for null. And it's not obvious. It's not a compilation error. It's completely valid syntactically. If we switch it to throwing the exception of the second example from before, and that basket.getFruit will throw the exception right away when it doesn't have fruit, we will know that right here is where the has check occurred. So the exception, or the error will be thrown on the line where the error occurred, not down several hundred lines later when you do a piece of fruit.eat when you call the method. So I'm just going to go back to the previous slide to stress that this exception is thrown somewhere else. The exception is caused by the top line. Whereas in here, the exception is thrown by the top line and caused by the top line. So it's misrepresented error. Null is not showing you where the error is. Now, changing pace off of null, now that I've bashed that for a while, we're going to talk about interfaces. Interfaces is a language or a language tool for declaring the design of a class without giving the contents. So it says it's very similar to UML in that you can say my class has these following methods, and in Java you can even give a default method that says this method uses the declared default methods, but I'm not going to talk about what kind of parameters or what kind of values are actually inside the class. Somebody else can worry about that later. And these are good in that now you can declare multiple interfaces that have certain properties and certain behaviors and mix them together. And the first thing we're going to talk about here is coding to the interface. You should not code to a concrete class. You should be able to declare an interface for your class, code to it, and then switch around different things that implement that interface. So for example, in class bucket, the top one, I have a private array list is my list, which is new array list. So that's a concrete class. An array list is something that implements list, but does it with an array very specifically. But I don't actually care that it's an array. All I want is a list. So I've got here private list, my list, is equal to new array list. And that means all I've declared when writing this is that I care that's list. I don't care how the list was implemented as an array, and I don't care about using the extra methods that maybe array list has introduced. And what this allows you to do is switch out array list without having to refactor the rest of your code. So now we can switch it with tree list. And we've now got private list, my list equals new tree list. Because we use list, we know that the rest of our code only uses methods from that interface. And thus, when you switch it to tree list, it still only uses methods from that interface. It doesn't care what else it has. So whenever possible, pass in or return interfaces. Now I have included this. This is the first of two design patterns that I'm going to introduce. And the reason I've shown this one is because it's a very good example of interface use. This is a strategy pattern. And what the strategy pattern means is I've got an algorithm that I want to do something, or I've got several algorithms that do the same thing. So I have declared an interface called, in this case, strategy, iStrategy for interface. And it has a method called behavior. Returns void, and it's public. Strategy 1 is some sort of concrete class that I've coded, and it has a behavior. Strategy 2 has a behavior as well, coded differently. And strategy 3 has it also coded differently. So you will have a class that says uses strategy. So you'll have a use strategy, which actually calls behavior. And you have set strategy, which will set whatever strategy you want. This is just a very straightforward way of using interfaces. Looking at it from a more code point of view, you would declare an interface iStrategy, which has one public method, void behavior, and in the three of them you would have some behavior declared. When you call it, class uses strategy, it would have the two methods, set strategy, this.strategy is equal to strategy, whatever you pass in, and use strategy. So something in here will use the one you set. Now, I always thought that use strategy might be a little misleading. It could be any methods or a number of different methods that might use the strategy. This was just to keep it clear that the strategy pattern means that you haven't defined the algorithm, or you haven't defined the behavior of the algorithm, the implementation of the algorithm ahead of time. You have only declared its behavior. Which brings us to the second pattern. And the second pattern deals with what's known as immutable objects. And that is, it's a good practice that classes should be immutable unless there's a very good reason to make them mutable. If a class cannot be made immutable, limit its mutability as much as possible. What that means is when you create a class, if it can make it static, make it unchanging, then you know between accesses of that class, it's going to be the same. And they're simple to use, and they're easy to implement. When you do these, you don't need to copy or synchronize them. So if you access a completely immutable class, any number of different classes can have the exact same reference because it can't be changed. So they can't make any changes that affect the original. You don't need to synchronize on it because the data is not going to change. They make good keys because they are immutable, they don't change, and they are never in an indeterminate state. Ways of doing this is you can make classes final so that people can't add to them. Make all of the fields final and private. All fields should be final and private by default, unless for some you have good reason not to. You can easily not provide accessor methods. And of course, you can set the values in a constructor, which is also known as a factory design pattern. You can also use an immutable pattern. And the idea of a mutable pattern is that sometimes you have a mutable class that you want to be able to protect, you want to be able to restrict access to. So instead of passing it around or returning it and hoping that you don't make changes, this is typically protecting you from yourself. What you do is you have an immutable interface. So you'll declare all of the getters, not the setters, in the class. So get flavor, get color, get shape are getters. And then your public class, or sorry, the class that implements immutable fruit will implement the gets, but they will also have some classes that will change the state of the class. So none of these would change any of the internal variables. All they're doing is looking at it. And what you can do with this is you can have one class, or you can be encapsulated in one class and be able to change it so it becomes immutable. But when someone wants to look at it, you can collect all of the getters into one spot, keeping your code clean. Return the immutable part because it implements immutable, and voila, you have safety around your code. That is it. So there are some things that I've used to source this. So thank you for attending.